Calculus 1, BSIE 1A, Charlie Team. Before we formally start this video, I encourage everyone to stay relaxed, have focus, and let us learn more.
Good day! Welcome to Charlie Team Tutorial. Today, we're diving into the fascinating world of parametric equations. Understanding parametric equations. Parametric equations are a powerful mathematical tool and a core aspect of numerous advanced mathematical and scientific studies. But before diving deep into this concept, let's start with the basic understanding of what a parametric equation is. Definition: parametric equations are a set of equations that express the coordinates of points in a system in terms of one or more parameters. Simply put, they allow you to express both the x and y components of a function as a function of a third variable, often denoted as t or theta. Example: for instance, you might have a parametric equation where x and y are both expressed as functions of t, like this: x equals t squared, y equals t plus 2. In this case, t is the parameter. Now let's dive deep into its applications. They are commonly used to describe the motion of an object in physics, the path of an object in three-dimensional spaces, and in many areas of science and engineering. In more real-life applications, parametric equations reveal themselves to be extremely useful. For instance, if you're into animation or game development, parametric equations can be used to model the path of an object flying through the air or bouncing around on a screen. They can also be used in computer-aided design or CAD to construct curves and shapes with specific properties. So, even if you're not a math enthusiast, you can still have fun with parametric equations. Now let's understand the derivative of parametric equations. In the world of parametric calculus, the derivative plays a crucial role in conventional calculus. However, finding the derivative of parametric equations introduces a bit of a twist. But don't worry, the process is simple when you break it down into steps. The derivative of a pair of parametric equations, say x equals f of t and y equals g of t, is essentially the derivative of y with respect to x. However, since x and y are both functions of t, the rule of chain derivation comes into place. The formula of deriving the parametric equation is dy over dt over dx over dt. Now let's have an example. Now let's go through to our first example given. X equals 8 plus t squared, y equals 4t squared minus 5t raised to the power of 4. Now let's differentiate x, or let's find the derivative of x with respect to t, since t is the third variable being used. Now let's write dx over dt. So, since 8 is constant, so it is 0 plus 2 times 1t equals 2t, 2 minus 1 equals 1, so no need to write the exponent 1. So, the derivative of x is 2t. Now, let's find the derivative of y with respect to t. So, 2 times 4 equals 8t, 2 minus 1 is 1, so no need to write the exponent 1, minus 5 times 4 equals 20, t, 4 minus 1 equals 3, so we're going to write the exponent 3. Now that we already find the derivative of x and y, now we apply the formula dy over dx equals dy over dt over dx over dt. Now let's substitute the values. Dy over dt equals 8t minus 20t cubed over dx over dt, which is 2t. 8t divided by 2t equals 4 minus negative 20t cubed divided by 2t equals negative 10t squared, since exponent 3 minus 1 equals positive 2. Now this is our final answer. Now let's move on to our next example. Now this time I want you guys to try answering it. Comment down your answers. Let's solve it. First, we're going to find the derivative of x and y. The derivative of x is 3t squared. 3 times 1t equals 3t. Exponent 3 minus 1 equals 2. The derivative of y equals 6 times 2 equals 12t. Exponent 2 minus 1 equals 1. No need to write the exponent 1. Minus 15 times 3 equals 45t raised to the power of 2, because exponent 3 minus 1 is equal to 2. Now that we already get the derivative of x and y, we are going to use the formula of finding the derivative of parametric equation, which is dy over dx equals dy over dt over dx over dt. And then substitute the value of dy over dt, which is 12t minus 45t squared, over the value of dx over dt equals 3t squared. (12t divided by 3t squared is equal to 4t raised to the power of negative 1, because exponent 1 minus 2 is equal to negative 1, minus 45t squared divided by 3t squared is equal to 15, since exponent 2 minus 2 is equal to 0. Let's simplify this. We're just going to put the t as the denominator of 4 to make it positive. So 4 over t minus 15. So this is the final answer of example number 2. Let's dive deep on our example number 3 involving trigonometric functions. Given x equals 4 sine t, y equals 12 cos t. Derivative of x, copy 4, and find the derivative of sine equals cos, and copy t. Now, let's move on to our y. Copy 12, then find the derivative of cos, which is negative sine, then copy t. Next, multiply 12 to negative sine t equals negative 12 sine t. Now let's derive the parametric equation using dy over dx equals dy over dt over dx over dt. Then substitute the values. Negative 12 sine t over the derivative of dx, which is 4 cos t, equals negative 12 divided by 4 equals negative 3 sine t over cos t is equal to tangent t. So this is the final answer. Guys, try answering this fourth problem involving trigonometric functions. Comment down your answers. Let's solve it. Let's derive x dx over d theta. D theta, because we're going to differentiate x with respect to the third variable being used, which is theta. Copy 3. The derivative of secant is sec u tan u, so sec theta and tan theta. Copy 18. Then the derivative of tan is secant squared u or secant squared theta minus 5, since 5 is constant, so 0, and the derivative of y is 18 secant squared theta. Let's substitute the values. 18 secant squared theta over 3 secant theta tan theta. (18 divided by 3 equals 6. Cancel secant squared and secant theta, remaining secant theta over tan theta. Let's simplify. We get 6 cosecant theta. Did you get it right? Very good. Now let's move on to our last example. X equals cos cube theta, y equals 4 sine cube theta. Differentiate x and y with respect to theta. Now apply the formula dy over dx equals dy over d theta over dx over d theta. Then substitute the values of dy over d theta over dx over d theta. Twelve divided by 3 equals 4. Then cancel sine theta and cos theta. Then copy 4 sine theta over cos theta. Then copy the negative sign. And then simplify, we get the final answer, negative 4 tan theta. And that's all. Thank you for listening and watching Team Charlie tutorial. Now let's take a recap of the topic parametric equations. In summary, parametric equations has served as a crucial mathematical tool integral to many advanced fields of mathematics and science, and some of its real-world applications are in physics, engineering, and in CAD or computer-aided design. Also, parametric equations consist of a group of equations that define the coordinates of points within a system using one or more parameters. In simpler terms, they enable the representation of both the x and y values of a functions as functions of a third variable commonly referred to as t or theta. In conclusion, parametric equations are a vital mathematical tool that enhances our ability to model and visualize complex relationships in both theoretical and practical applications. Their flexibility and applicability make them indispensable in mathematics, science, engineering, and computer graphics. In finding the derivative of parametric equations, we apply the formula dy over dx equals dy over dt over dx over dt, and then differentiate x and y with respect to t or theta, then substitute and simplify to get the final answer. Now let's end this tutorial with a quote of Bertrand Russell saying, "Calculus required continuity, and continuity was supposed to require the infinitely little, but nobody could discover what the infinitely little might be."
And that is the end of this video. Thank you so much for watching, and I hope that you had a great time and learned a lot from watching. Please don't forget to subscribe to our channel.